In this video, we're going to revisit the major ideas from Chapter 3 by working through some examples. We're going to talk about the classical approach to probability. We're going to talk about complementary events and the probability rule that goes along with those. And we're going to talk about mutually exclusive events and the special addition rule. Let's start with a quick review of the classical approach to probability. The probability of an event A is the number of outcomes favorable to A divided by the number of outcomes in S, where S is a sample space comprised of equally likely outcomes. As long as you've got a sample space with equally likely outcomes, you can just count the number of ways A occurs in the sample space, divide by the total number of outcomes in the sample space, and that's the probability that we assign to the event. For our first example, we're going to look at the experiment of rolling 2 dice, and I've got the sample space here on the screen. To make it easier to read, the person who created this picture colored the dice different colors, but of course the color of the dice doesn't matter. You can see that there are 6 different ways the red die can come up if you go down a column. There's 6 different ways the white die can come up if you go across a row. And so this sample space has 36 distinct outcomes. If we use the assumption that the dice are fair, then we can use this sample space to come up with probabilities because all 36 of these outcomes would be equally likely. So let's look at a couple of examples. Let's find the probability that you roll doubles. If you're not familiar with that term, rolling doubles means that the dice match, that you roll a pair. So our rule says that the denominator of our probability is the number of outcomes in the sample space. And we said that there are 36 outcomes in this sample space, so the denominator of our probability would be 36. The numerator of your probability is the number of outcomes favorable to your event, which basically just means the number of ways your event can occur in the sample space. So we have to find all of the outcomes in the sample space that represent the event rolling doubles. That is where the dice match. And if you follow this diagonal from the upper left-hand corner down to the lower right, you can see that there are 6 different outcomes that represent rolling doubles. And so the numerator is 6. And that's our probability, 6 over 36. I don't care if you reduce, but this fraction does reduce down to 1/6, and that might be a little bit easier to interpret. You roll doubles 1/6 of the time. We could also turn this into a decimal. That's 0.167 approximately. I had to round that. We could turn that into a percent, 16.7%. If I asked for an exact answer, you'd have to give me the fraction. But if the instructions don't specify that you have to give an exact answer, then I would accept the decimal or the percent. Any of those answers would be okay, unless you need an exact answer because those last 2 were rounded. Let's do another example. Using the same experiment of rolling 2 dice, let's find the probability that you roll a sum of 11 or more. So you're playing some game, and in order to win, you have to roll an 11 or higher. Let's find the probability that you're going to win that game. We know that the denominator is going to be 36, because there are 36 outcomes in the sample space. How many of the outcomes represent our event of rolling an 11 or more? Well, we've got this 5 plus 6, that's 11. We've got 6 plus 5, which is 11. Those are distinct outcomes because you got different numbers on the red die and different numbers on the white die. And then the boxcars, the 6 and the 6 in the lower right-hand corner. So that's 3 outcomes that satisfy the definition of our event. 3 favorable outcomes. So the numerator is 3. And that reduces to 1/12. And you could change 1/12 into a decimal and convert that to a percent. I'm not going to go through that again here. But that's the probability of rolling an 11 or more, 1/12. Or 3 over 36. Remember, I don't care if you reduce. Let's do one more example with this experiment, but we're going to do the problem in a slightly different way. Rather than counting through the sample space, I'm going to show you an alternative that we can use in certain situations. This third example says, find the probability of rolling a sum less than 11. Now this sample space isn't that big, so I guess we could just go through and count all of the sums that are less than 11. But I want to show you a more efficient way to do this problem. And the idea here is that it's actually going to be easier to work with the complementary event. The complement of an event is basically the opposite. And the opposite of rolling a sum less than 11 would be rolling a sum of 11 or more. which we already know the probability of. We just did that example. So now we just have to remember how the probability of an event and the probability of the complementary event are linked, and that comes from this rule. The probability of an event is 1 minus the probability of the complementary event. So when it's easier to find the probability of the complementary event, this rule comes in really handy. And that's what happens here. The probability of rolling a sum less than 11 can be found by doing 1 minus the probability of the complementary event. And what is the opposite of less than 11? It's not greater than 11. It's greater than or equal to 11. That is, rolling a sum of 11 or more. The opposite of less than 11 is 11 or more. And we already know that probability. We just found it. The probability of rolling a sum of 11 or more is 1/12, 336. Even if we hadn't already calculated that probability, it's just easier to count the number of ways to roll a sum of 11 or more than it is to count the number of ways of rolling a sum less than 11. So this would still be a wise approach even if we hadn't already found that probability on the previous slide. As it happens, we already do know this probability, so we can just proceed using the knowledge that we picked up in the previous example. We know that the probability of rolling a sum of 11 or more is 1/12, so this is 1 minus 1/12. And to subtract those, we need a common denominator. 1 is 12 over 12. And then 12 minus 1 is 11, so this is 11/12. And again, you could argue that we didn't need to use this rule here because the sample space is so small. But I wanted to demonstrate the complement rule because it will come in handy in the future where the experiment has too many outcomes in the sample space to make counting realistic. Like here we only rolled 2 dice and so there were only 36 outcomes. If I change the experiment to rolling 5 dice, there are 7,776 elements in the sample space. And in a situation like that with a really large sample space, oftentimes complements come in handy. So just keep that in mind. Let's change the experiment. We'll stay with the classic. We're going to flip coins. This time we're going to look at flipping a fair coin 3 times. So I've got the sample space already listed here. This time I didn't get a pretty picture for you. I wrote it out myself. But if I use H to represent heads and T to represent tails, then one possibility is that the coin comes up heads on all 3 flips, which I've represented by HHH. This second outcome means that it came up heads on the first flip, heads on the second flip, but then tails on the third flip. And you can go through and see that I've got all of the possible outcomes. There are 8 total elements in that sample space. My first example says, find the probability that you get exactly 1 tail. We said the sample space has 8 outcomes. And because the coin is fair, they are all equally likely, so we're not violating that part of the rule. So the denominator of our probability is going to be 8. The numerator is the number of outcomes in the sample space which are favorable to the event of exactly 1 tail. So let's go through and find all of the outcomes that have exactly 1 tail. HHT has exactly 1 tail. HTH has exactly 1 tail. I need to skip over HTT because it has 2 tails. THH has exactly 1 tail. And all of the other ones have more than 1 tail. So there are 1, 2, 3 favorable outcomes. And so that probability is 3/8. That converts to a terminating decimal, that's 0.375, and that of course can be rewritten as the percentage 37.5%. And if I asked for an exact answer in this problem, you could give me any of those 3 answers because they are all exact. None of those are rounded. Let's look at another example. Same experiment. Find the probability that you get at least 1 tail in these 3 flips. At least 1 tail means 1 or more. If you're not comfortable with that phrase, at least 1, that means 1 or more. I know least sounds like you're saying less, but when I tell you you have to get at least a 90% in my class to get an A, that means 90% or more. Or if you were selling your car, and you said, I want at least $1,000, and your friend came up to you and said, well, I'll give you 800, you'd say, no, moron, I said at least 1,000 or more. So at least 1 means 1 or more. And we could go through and count all of the different ways that you get 1 or more tails. But I want to demonstrate this with the complement idea. The complement of at least one is none. If you don't have at least one tail, then you have no tails. So we could do this by doing 1 minus the probability of no tails. And of course, it's easy to count the number of ways that there are no tails. There's only one outcome out of the 8 that has no tails. And now we get a common denominator. And we subtract. And we get 7/8. And some of you might argue that it would have been easier to just go through and count the 7 different outcomes that have at least one tail. And I can't argue with you. That might be easier. But I want to demonstrate the idea because we're going to need this in the future. One more example, let's hit one of the special cases. Same experiment. Let's find the probability that when you flip a fair coin 3 times, you get less than 6 tails. Now, if you think about this logically, you can come up with the answer automatically. But we can still use the sample space. There are 8 outcomes. And let's see, this has 0 tails, that's less than 6. And this has 1 tail, that's less than 6. 1 tail, 2 tails, 1 tail, 2 tails, 2 tails, 3 tails. They all have less than 6 tails. And of course they all have less than 6 tails because you're only flipping the coin 3 times. The maximum number of tails you can get is 3. So all 8 of these outcomes have less than 6 tails. So this comes out to 1 over 100%. You could leave your answer as 8 over 8. 8 over 8 is 1. That's the correct answer. You don't need to convert it. In these special cases, I like to simplify as a reminder of these boundaries on probability. This is the largest number that can be assigned to a probability, 1. And it signifies that the event is guaranteed to happen. It's a certain event. You always get less than 6 tails because the maximum number of tails you can get in 3 flips is 3. Okay, let's move on from the classical approach to probability and just focus on the complement idea. Here we've got an example that deals with cards, but you don't have to know anything about cards to answer this question. All the information you need is contained inside of the problem. It says a standard deck of cards is shuffled and 1 card is dealt from the top. The probability that this card is a heart is 0.25. What is the probability that the card is not a heart? The event the card is a heart and the event the card is not a heart are complements of one another. They're opposites. So to find our probability, the probability that it's not a heart, we can do 1 minus the probability that it is a heart. And again, maybe you don't know a whole lot about cards, but you don't need to know because we were told the probability the card is a heart. It's 0.25. And so we subtract. 1 minus 0.25 is 0.75. 75%. There are 2 things I want to point out about this example. One, you didn't have to know anything about cards in order to do this problem. Sometimes when I do examples about cards or games, people get uneasy because they don't know a whole lot about the topic. But I promise you any information you need will be given in the problem. Like maybe you didn't know that 1/4 of the cards in a standard deck are hearts, but you didn't have to know that because I gave you that information in here. The other thing I wanted to do in this example is demonstrate one where the probability was given as a decimal, which is a valid format for a probability as long as it's between 0 and 1. We've done so many examples with the classical approach to probability that you think of probabilities as being fractions, but you can be given a decimal or a percent, which is what I did in the next example. Maybe this scenario is something you can relate to. You and your significant other can't pick where to eat, so you let fate decide by having a website choose a local restaurant at random. If 63% of the options on the site are fast food, what is the probability that the site will land on a restaurant that is not fast food? Maybe you can see this answer immediately, but I'm going to approach this with our rule. The probability that it's not fast food is directly related to the probability that it does pick fast food, and that's given. We're told that it's 63%. I'm going to use that same complement rule, but because the probability was given as a percent, I would think of this as a percent problem. So I would do 100% minus the probability that it's fast food. That's 100% minus 63%, which is 37%. Same idea, but rather than converting the percentage to a decimal or a fraction first so that I could use the standard version of the rule, I just converted the 1 to 100% and then subtracted the percents. And I'm guessing that's how you would do it too. I'm also guessing that you wouldn't write out all of this formality here, and that's okay. If you wanted to show your work, you could just show the part where you subtracted. Okay, one last example, and in this one we're going to demonstrate that special addition rule. Let me read through the problem first, and then we'll talk about the concepts. In my favorite music playlist, 2/3 of the songs are from the 1990s, and 1/6 of the songs are from the 1980s. Suppose I shuffle my playlist to randomize it. What is the probability that the first song played in my playlist is either from the 1980s or the 1990s? Okay, so we're being asked to find the probability that it's either from the 80s or from the 90s. How can we find that probability? Well, we have a special addition rule that applies to mutually exclusive events. And these two events are mutually exclusive because if a song comes from the 80s, then it didn't come from the 90s. And if a song came from the 90s, then it didn't come from the 80s. These events are mutually exclusive. You can't have a song that was simultaneously from the 80s and the 90s. Now I know you could be a smart aleck and argue that there were songs from the end of the 80s that were also popular in the 90s, or that a song can be re-released or covered. But you know what I mean. I mean that version was released in that year. If we assume the two events are mutually exclusive, then we can apply this special addition rule, which says that the probability that either A or B occurs is equal to the probability of A plus the probability of B. That is dependent on the two events being mutually exclusive, but we've said we can assume that here. So this is just the probability that it came from the 80s plus the probability that it came from the 90s, and that's 2/3 plus 1/6, which is 5/6. And I guess I should show you how I got that result. 2/3 plus 1/6 is fraction addition. I have to get a common denominator, so I can multiply the first fraction by 2/2. And I get 4/6 plus 1/6. And when you add fractions with a common denominator, you just add the numerators. And that's 5/6. If you're really uncomfortable with fraction addition, you can use your calculator to do fraction addition. So like for this example, I can type 2 divided by 3 to represent 2/3, plus 1 divided by 6 to represent 1/6. And if you hit enter now, it's going to give you a decimal answer. But after you hit enter, you can push your math key, and the very first option says change that result into a fraction if possible. And this one can be changed into a fraction, so the calculator does. Alternatively, you could stack that fraction command and it will give you the fraction without showing you the decimal at all. So if you just want to double check your fraction arithmetic, or if you feel really uneasy about it, go ahead and use this calculator command. That way you'll feel a little more comfortable. Okay, that covers all of the ideas I wanted to review. If you have any questions for me, shoot me an email or see me in an office hour.